So I guess we'll get started a little bit early so we can get to those cookies ahead of schedule, unless I go long. So if I start going long, you have to wave to me. All right, so this is practical statistics. I am a biostatistician. I don't have any competing, nowadays most talks need a competing interest or a slide. I don't have one, but 47% of all statistics are made up on the spot, according to the fortune cookie I got like 2 weeks ago. One of my worst habits, I don't know how I got in this habit, but I eat at those really terrible Chinese buffets that are like 3 pounds to get in all you can eat. You wait 6 hours hoping, don't throw up, don't throw up, don't throw up. And so, but I go to these all the time, and actually had a actual fortune cookie. 42.7 are all made, and that might actually be right. So I'm going to angle this talk from sort of the same two perspectives, kind of the same one really, and that is of a reader or someone who is assessing manuscripts, not so much as someone who is writing statistics or doing research and needs to write statistics. So this is from the perspective of someone, a practitioner reading a paper, wanting to see if they should change their practice patterns because of the manuscript. And also, for our new journal, which is going to be sort of introduced this afternoon, we're going to publish in their knowledge summaries, which are short critical appraisals of the literature, addressing a focused clinical question. These are usually not very long and don't take very long to do, but in order to do that, they do require, appraising a few manuscripts. And so this talk is sort of leaning that direction. Now, I'll talk about 4 different things this afternoon. How research statistics are different from reader statistics. So how the researcher is just going for a different target than what you want to see. I'll talk about the role of p-values in an article, the clinical value of an article, and the evidentiary value of an article. So I'm going to use one example sort of throughout the whole talk, and it's from this paper. And so this is where we start, where researchers versus readers, kind of a thing. And it's the comparison of lateral fibellar suture and TPLOs for the treatment of dogs with cruciate disease. My wife is the first author on this paper. This is her randomized clinical trial that was published in 2013. So this is, I'm going to use this as an example of how she is different than us, sort of a we versus them sort of a thing. So just so we're all on the same playing field here, just a quick background, TPLO is an osteotomy procedure. So when I talk about TPLOs, this is 40 of the dogs got those. It's a randomized controlled trial. So 2 groups of 40 in each. 40 got the TPLOs and 40 got an extracapsular procedure. So that particular one, the lateral fibellar suture. And I usually call them TPLOs, and these I just keep changing the name on, extracaps or whatever. But anyway, that's the 2 procedures. And then the other thing I'm going to talk about is, as our outcome, she measured several outcomes, is going to be peak vertical force. If you're not familiar with peak vertical force, it's the maximum applied during maximum force applied during stance phase. So you're walking, you're loading, and then boom, this is the peak force. So anyway, that's when I talk about peak vertical force. That's what I'm talking about. This pressure. We measured as a percent of body weight, so you can compare dogs to some extent, and we'll be talking about it at the trot. So anyway, this is the results, the main results of the paper. Remember, we're looking at this from a reader's point of view, and we can point out a few things here. First of all, the squares. This is the TPLO group over time, and this is the extracap group over time. And we're just going to fix it 12 months because really, I've been involved in a lot of these studies, and people measured these out. It's quite interesting, but really, what you really care about is, at the end of the day. Are the dogs better or not? So anyway, so in this paper, we have, and I'll refer to these too, at 12 months, the peak vertical force, the TPLO group on this hind leg was 48% of their body weight, and in the lateral fibellar suture, it was 37%. So that's kind of where we're starting with this. Now, here's where it sort of starts to diverge. She put asterisks over 2 of these to indicate that that's where the groups become statistically different, significantly different. And so the idea is that we're reading this paper, we read that, it's significantly different, and we've got to figure out exactly what that means, because I think that in a lot of cases, I'll show you later, we don't even know what it meant when we wrote the paper. So in order to do that, we have to start way back to the difference between population parameters and sample statistics. Because really, let me go back, the researchers are interested in this, and we are really interested in this. And they'll focus on this when we want this. If you can imagine a large population of, I guess she probably did Labradors, but I'm not sure. So I don't remember. So imagine a large population of Labradors with TPLOs. She sort of sampled 40 of them. Now, that's the conceptual thing of the way a statistician would think about it. Of course, she had all these dogs that were lame, randomized them. But in the mathematical construct that is this, you think of this big population of all Labradors that would have TPLOs, for example, and then she would have a sample of 40 of them. And what Wanda, is my wife's name, Wanda wants to compare is, she wants to compare the population parameters, like the population mean. So there's a mean, just like there's a mean height for everybody in London, and if we're a sample, we have no idea, and we'll never know the average height of people in London. But we could find the average height of people in this room. So she found the peak vertical force of dogs in her study, but she can never know the peak vertical forces of the population of Labradors that have had TPLOs, or would have TPLOs too. So anyway, but she's interested in the population level thing. So it's important to note that your sample statistic, like your population, like the height of people in this room, is not the same as the height of people in London. Right? Whatever that number is, and we're a sample, we're not that height. And another sample in another room, of another lecturer, is going to be different. So it's always important to keep in mind that sample statistics are real numbers, they're fixed. They're the number, that doesn't change. And it's not going to be the same as, and that's actually probably statisticians and maybe physicists are one of the few groups of people that try and go sort of upstream. You know, an engineer, they'll stress the material and they'll say, okay, this is what it breaks at. But you know, we're trying to go from 40 to all. All right, so again, this is sort of repeating kind of the same thing, but in a little bit bigger picture. So Wanda's interested in comparing the mean of this population to the mean of this population, somehow using these samples. And again, even if these two groups had the same mean, you know, the average height, imagine the average height in London is the same as the average height in Liverpool, of all the people there. If you took samples out, even though they came from populations with the same average, they're not going to be the same. Those samples aren't going to have the same average. Right? It might be close, but they're not going to ever be the same. So in any study you ever see of interventions like this, these sample means will always be different. I mean, it's just the way that it works. All right, so we talk about p-values. Wanda had a p-value in there. So Wanda used a p-value. So we're talking about p-values now, to test if the two population means are different. So she's over on this side of the screen with those two big things. She wants to see if the population in London, is, their height is different from Liverpool, in this case TPLOs, so, and extra caps. So it's important to realize that a p-value is not a measure of the magnitude of the difference. It just says if there's a difference in those population means. That's all it is. So that's all a lot of researchers care about, is just, is my hypothesis that there's a difference, is that true? True or false? So this comes into the hypothesis testing p-value realm, and the magnitude of a difference comes into the clinical effect, which we'll talk about later. So here's how you get a p-value. And I was joking to some people later who saw the talk earlier that I've been describing how to get p-values for like 20 years now, and I've never been successful. So I'm not that optimistic now, but hopefully I'll convey the message I'm trying to convey, which is not to get you to necessarily how to do the p-value, because don't forget, we want to read about these and understand them, not necessarily calculate them, but it's very funny. So the idea is to assume a model that is the opposite of what you believe. So in the TPLO case, it's going to be, she thinks the two population means are different, so she would assume that, so she would assume the opposite of that they're the same. Then we check to see if the data are inconsistent with the model that we don't believe. So are the data consistent or inconsistent with the model we don't believe? And then, if the data are inconsistent, we reject the model in favor of the one we do believe. So this is one of the big complaints about, this is how it's done, is this sort of argument where you set something up, go through some steps. If your answer is absurd, that means your assumption was not correct. It's an old argument that goes way back to the Greeks, I think. And so the point is, this is one of the big complaints about p-values, and there's a lot of complaints about them these days, even by statisticians, is that is that they're just hard to get the mind around. So how Wanda got it was, like I was saying, assume the population means of the TPLO and lateral fibular suture groups are the same. Then we calculate a test statistic, which is simply the difference in the sample means, divided by something just to make it work. And then we know the distribution of that. And then we just see how odd that test statistic really is. So how it works is, if the population means are equal, then we expect the difference in the sample means to be kind of close together. So if the peak vertical force in the population of the TPLO group and the population of the extra cap group, if those are actually the same, procedures don't matter, then the samples are going to be different, but they ought to be close. That means that it ought to be under the hump of this distribution. It might be here, or it might be here, here, here. We would not expect it to be rare. This is like 1 in a million sort of a situation right out here. Right? So if it's out here, we say, oh, well, the only place that we get, so for answers out here, we think to ourselves, that can't be right. Because distributions mean everything's in the middle, usually, right? So if you get something in the tail, then, give me an example of heights again. Imagine we were measuring heights, and there was a height in there that was 8 feet. Well, we would probably think that was a mistake, right? Because there are 8 feet tall people, but it's so unusual that probably it was supposed to be something else. So, or better yet, maybe it was 58 feet, and it was really supposed to be 5 feet 8 inches. Anyway, get the point. So it's kind of crazy. So that's how it works. So what was interesting about this is that we actually wrote this wrong in the paper. When I say we, I mean her. So I was on the paper. So I cannot tell her this mistake because she'll go crazy and blame me because I should have checked it. So notice what she wrote here. Well, yeah, she did. The data are significantly different between groups. Data aren't different. Data are just the data. They're fixed things. Data can't be significantly different. It was the mean is 48 versus the mean of 37. They're just numbers. It's the population means were significantly different between the groups. So you'll see this pretty regularly, that the data are significantly different. That suggests that the person who wrote it doesn't realize they're actually talking about the population means, and they're thinking about these two numbers right here being different. These are just fixed numbers. They are what they are. These are obviously different. Right, and so that's an important thing when you're reading a paper, is now in your own mind, that even if you read data are significantly different, you can ignore that, and you realize that anything involving a p-value is talking about those population means, not about the data. But this is very telling because we want to know about the data. So sort of a mistake that was in some sense honest, that we'd like to think that these are really different. But we're not measuring that at all. P-values do not measure that. Effect sizes will. We'll talk about that in a minute. That leads to a pretty big mistake. Now, I'll give you some facts about p-values here. Sort of a long list of things about them. The classic 0.05 cutoff that maybe you've read about or seen is really arbitrary. So in the old days before computers, you would use tables that were discrete. Obviously tables discretized. And so 0.05 was just one of the numbers at the top of the table. So you looked to see where you landed, and if you landed below 0.05, you called that good. But they had like 0.01, 0.01, 0.05, and then 0.1. That's all the numbers on the whole table. And so, and the 0.05 itself, there's a great paper by Rosnow and Rosenthal, psychology paper, where they even say that surely God loves 0.06 as much as 0.05. And it's really true. And as Mark pointed out this morning, and I get these kind of phone calls all the time. Someone says the first thing they ask is, was anything significant, meaning it was anything below 0.05. And if it's 0.49, they're thrilled. If it's 0.51, they're sad. Well, really, it's a continuum. It's not a target. It's a measure. And so, now remember, we're doing this from the perspective of readers, of people reading it to maybe change their practice, or reading it to do a critical assessment. When you see this binary decision, less than 0.05 or greater, you should take it with a grain of salt. Because first of all, 0.05 is arbitrary. And partially comes from just the days before computers. So, and what happens is that the authors, like Wanda, where she put those asterisks over those two on that chart, they're going to drive the discussion of the paper from what's significant. And that, for other reasons coming up, that could be just misleading. So another thing is Fisher, who invented p-values, did not consider them the final word and didn't consider 0.05 unique. So we're sort of using p-values off-label now. Wildly off-label, actually. And he just thought it was one more way to convince people that this sort of hypothesis was okay or not okay. Just one tool in the toolbox, not the way we do now. Another thing that it's really an easy mistake to make is that a p-value is not the probability that the hypothesis is true given the data. It's not that. Because the p-value is a probability, and if it's small, they think it's the probability of the null hypothesis just being true is small, so we reject it or something like that. Nope, it's actually the probability of the data given the hypothesis. So it is really is the data consistent with this hypothesis, so it's a different way of looking at it. Regardless of the difference between those means, p-values get smaller with increased sample size. So there was a great in that same Rosnow and Rosenthal, he talks about two doctors, Dr. Jones and Dr. Smith. Dr. Smith compares two groups, A and B, and shows that there's a difference and that B is superior to A. Dr. Jones invented A, and so he doesn't like that result, so he replicates the study with half the sample size and fails to find a result because the p-value is now above 0.05. The clinical effect is exactly the same. The magnitude of the difference is the same, but you can fail to show an effect by, or fail to show a significant statistical effect by a smaller sample size. Already said that, and now another important one, and this is something that is one of the biggest misconceptions, is that when you do see a p-value above 0.05, a lot of people will treat that as the groups being equal. So back in Wanda's case, she had these TPLOs in the extra cap group and collects her data, blah, 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 and then gets a p-value. Now, if that p-value were greater than 0.05, many people would say that there's no difference between those group means. And hopefully they'd be population group means. That's not true. That's a different statistical test that we rarely do in veterinary medicine. All you fail to do is you just don't have enough evidence to conclude anything. There's not enough data to conclude to reject that hypothesis. So if you see this and someone says, oh, the groups are the same, they're not the same. They're just not. They might be. They don't know. So again, you're reading the paper, you're doing some critical assessment. They probably have some p-values below 0.05 and some that are above 0.05. And if they say, well, the groups weren't different on this variable, and it's at 0.06 or something, well, no, they might be. You just failed to show that they're different, that's all. Now, I think I've maybe failed to convince you that p-values are awkward, if nothing else. All right, we know that they're hard to get the mind around. This is a very interesting slide. So the problem is it's also more than one correct analysis. So this 29 research teams were given the same set of data and asked to determine if referees were more likely to give red cards to dark-skinned players. So 29, competent research teams given the same set of data, asked to do an analysis to see if in soccer they would get red cards were more likely to be given to dark-skinned players. Every research group got a different answer. The green ones are where they were statistically significant. The gray ones where they weren't. But even so, the intervals are different length, and these are sort of the means, the green dots. So you can see it's a huge interval here, and that's there. So they're completely different. So the point here is that you're reading the paper, you're worried about the p-values. Did they pick the right statistical test? Don't worry about it, really. Don't worry, because 29 valid analysis of the same data, and there's different result. So certainly you can make mistakes doing statistics, but there's also a lot of right ways to do it too. And it's just not worth getting as a reader and as someone critically appraising it. now is where you put your own expertise, your own knowledge about the subject. Sort of, okay, you take this with a grain of salt, that's fine, and you press on. It's even more damning for the way that researchers do statistics. Andrew Vickers looked at the human journal Urology and found 16 wrong analyses before he found a correct one. So he just started looking through them. Different papers, wrong, and then found a right one. This classic paper from Science sort of showed that most published research is wrong. They do this by looking at p-values. And you can see one of the ways they do it is by looking at p-values. And what they'll do is they'll make a graph of p-values that they send out software to journal sites, and they can just pull off p-values, and they can show sort of a uniform distribution of p-values above 0.05, like 0.1s, and they're sort of all the same, which you would expect, and then this huge leap at 0.05, where people are using various techniques to make sure their p-values get below 0.05. And then this was just this year, it was a great study. They took 100 psychology experiments, so classic ones, and reproduced them exactly, and they could not reproduce 60% of them get the same answer. So the point is that when you get a manuscript or an article and you're reading it for a critical assessment or reading it for whatever the reason, is really you've got to look at it and, again, use your own clinical expertise as well as what the author says. Because remember, their goal is to get a p-value below 0.05. Said that, yeah, and definitely don't let p-values guide your understanding of the paper the way the authors have. Okay, so that's p-values. Kind of not very cheering news. Yeah?
Could you just say again what p-values are used for?
Yes. Sure. P-values are used to test a hypothesis. They're a measure of how the data compare to a hypothesis. It's a probability value. If that probability is low, that means that hypothesis is not correct and does not agree with the data very well.
What is less than 0.05 mean?
So that's a very small value. That would mean that okay, here's what that means. That would mean that the probability of observing a value more extreme than the one you've got is that p-value under that hypothesis. So for the TPLO example, the hypothesis is that, so Wanda's hypothesis is that these groups are different. To calculate the p-value, we actually assume that they're the same. All right? We get this p-value from the data, and what the p-value tells us is the probability of observing a value more weird than the one that we've got. So if the p-value is below 0.05, there's only a 5% chance. If we were to repeat the experiment again, there's only a 5% chance of getting a p-value weirder than the one that we got. And that 5% is the cutoff that we use. Does that sort of help?
Yeah. Okay.
Thank you. Oh, yeah, okay. So magnitude of the effect. So that's p-values. So again, I guess the take-home there is just don't let those drive your assessment of the paper. This should drive your assessment of the paper, in my view. In fact, there's one psychology journal that now is banning p-values because they're too easy, because they're just too easy to get below 0.05, and they just want to do this kind of stuff, effect size. So what's the magnitude of the effect? Now that you know the p-value, let's say we believe the p-value, and then the statistics was fine, and you're happy with that. It's okay. I mean, they're not, that's great. So you go with that. What's the, really, now that, say Wanda's come up with a p-value below 0.05, is it worth, you've done extra caps your entire career, and now is it worth doing TPLOs? Because probably most people do TPLOs now. They do in the States anyway, but let's say, is it worth switching? Well, last year, a study of more than 19,000 people showed that those who met their spouses online are more likely to have high marital satisfaction than those who meet offline. All right? So good news, bad news. I don't know. We're saying, did you meet your girlfriend online or offline, Henry?
Offline.
Oh, dang it. Okay. Sorry. now you've got your answer. So, okay. So, yeah, right. Okay, so the p-value is way out here. That means that, again, the probability of observing if we have the data weirder than what we've got is quite small. So that means our data is so weird that it can't be the case that the online and the offline are the same. I'm telling you, p-value is tough to get that over. All right, but the clinical effect is tiny. Happiness moved from 0.48 to 5.64. So really, although there's this clear evidence that online, meeting your spouse online is a little bit happier, you wouldn't all of a sudden switch from going to bars. There's a lot of reasons not to switch to online from bars, but one of them is meeting your spouse there. So this is why it's so important to look at effect size. Effect size. Okay, so I'm going to give this slide a few more times, so it'll sort of build up on itself. But for now, effect size is a way to measure the magnitude of what's going on. It's often given by two numbers, a D or an R, and I'll talk about those in a second, D and R. But you get this weird number out of here, and you might think, well, what help is that? You know, you've got this TPLO study, and your effect size is 0.6 or something, right, whatever it is. Well, that doesn't tell you any more than Wanda's 48 to 70 to 37 difference in means. However, effect sizes have interpretations that can be helpful. So Cohen is a great psychologist. He benchmarked these with large, medium, and small effects. Cohen was a really smart guy. Another way he did it too is he would take the effect size and he would match it up with something different that people would understand. So the way he explained 0.2 was the difference between heights in 15-year-old girls and 16-year-old girls. So he found the effect size of that, and then whenever he did a study and he got something like a 0.2, he'd say, well, it's kind of like the heights between the 15-year-old girls and 16-year-old girls. Which, there's got to be a height difference there, but it's got to be so close and so much variability that you really can't discern the difference. If you had a crowd of teenagers, you would not be able to really pick out the 15-year-olds from the 16-year-olds from that. So it's a handy way to do it. They can be converted. These online calculators will convert these for you, but you can convert them to numbers needed to treat, which is the number of subjects you have to give the intervention to before you get one beneficial effect. So that, there's some other convenient sort of interpretations as well, but the idea is that you look at these effect sizes. So here's another example of effect sizes. Over in America, we'll do anything to help our health except exercise and eat properly. And so taking a pill seems like a great way to go. And so we're big on taking aspirin to reduce heart attacks. I don't know if you guys do the same thing over here, but you take aspirin to reduce heart attacks. So there's this huge study, physicians' health study, where they took 22,000 physicians. Half of those took aspirin and half took a placebo. And then they just counted the number that had heart attacks, had MIs in particular. And it's pretty clear that the placebo group had more. And the p-value was quite small. There's an undeniable difference between the population proportions. So no doubt that there's a big difference there. Well, see, I just misspoke, right? Nobody threw stuff at me. We know there's a big difference. So for sure, the population proportions are different. We just don't know how different. So we know there's a group difference here, for sure. And right there, that's where the researcher is happy. So we have to go ahead and ourselves calculate the effect size, which I did, which is 0.06. So you'd have to treat 40 people with aspirin to get one beneficial effect. And we'll go back to that grid slide in a second, and we can look at that. But so the NNT, typically below 6 or 8, below is considered effective. So you can see this is really ineffective. And there are 16,000 gastric bleeding hospitalizations a year in the United States. So really, when you throw in the complications, it's probably not a great idea to take aspirin, even though, we still see the ads on TV. They tell you to go see your doctor, but you don't need to see a doctor to take aspirin, so you just go to the store and take aspirin. And so that, you can see way down here was right about here was that 0.6 small, and I calculated a different number needed to treat. So let's look at Wanda's effect size, because I said earlier that she's not going to give that to you. And so we've got to have to do it ourselves. And maybe not for every variable in a paper, but maybe for the important ones. Peak vertical force is certainly one of the most important orthopedic outcomes. So I'm just going to show you how to do it, that at least maybe convince you that it's not hard. And again, there's online calculators for this, so you don't have to do it on the back of an envelope the way I do it. But the formula that D number is just this. It's just the mean of experimental group minus the mean of the control group divided by the standard deviation. So it's a very simple formula. And I just read this off her graph, pretty much. And I'll give you pretty much. So I just kind of read off, again, this, if you're reading off a graph, you don't think that's accurate, it's accurate enough. I mean, if you can't read it off the graph, if misreading the graph is going to make you make a mistake in your decision about whether or not to do this in practice, probably it's not clinically significant. You know what I'm saying? I mean, it's, you know. So anyway, we read off the 48, read off the 36 off that graph. I took the difference, like the formula said. The standard deviation is 6. I'll tell you about that in a second. I calculated it, and I got an effect size of 2. We go back here. It's so good, it's not even on the table. So I went to an online calculator. You know, it's way up here in a large effect size, and it gives an NNT, number needed to treat, of almost 1.5, which means that you don't even have to go to 2 patients to get an effect. So TPLO is really much better at 12 months on those type of dogs, which are medium to large breed dogs. I don't think she did small dogs in that study, than the extracapular procedure. So here it's undeniable that that's the way to go. Both the p-value being significant, sorry, the group means being different, and the big effect size. So the take home for this part of it is that effect sizes give magnitudes, give the magnitude of the effect. Said that. Small effect size means the treatment has little clinical value regardless of the p-value. So that's like that aspirin example. Phenomenally small p-value. I'm sure the researchers were ecstatic, but not worth doing, probably. So this is the part where every statistician feels obliged to do some calculations just to make it look hard, even though it wasn't that bad. So people often ask me, what's the difference between a standard deviation and a standard error? And when should you use the both? So you're reading the paper, and you know the reviewers are going to report, the authors are going to report a standard deviation or standard error. And how do you even know if they're reporting the right thing or something that's useful? Well, they're related to each other. The standard error is just the standard deviation divided by the square root of the sample size. So one had an n of a total n of 80, but in a group of 40. So it's just 1 minus that. Take the square root of it. And that's how you get the standard error. She reported this. I'll show you that. So I just had to multiply that over. And I'll talk more about those in a second. So yeah. So yeah, she reported the mean plus or minus the standard error of the mean, or standard error. This is the same as the standard error. So I just read these off the graph, and then I multiplied. So I read this off the graph, multiplied this thing here by the square root of 39, and I got my standard deviation. So you're going to want to plug this into some software, like on the web, and there's lots and lots of them. But you see, it's really not too bad. So what is the standard deviation anyway? Well, if you're reading a paper and they report that, it's roughly the average distance from the data to the sample mean. So it's just a measure of the spread or the variation of peak vertical forces. So then what's the standard error? Well, the standard error is the same thing as the standard deviation, but for sample means. So this is really confusing because it's pretty easy to imagine a standard deviation. You got these 40 peak vertical forces. You can imagine them on a number line, and you can imagine how kind of some are far and some are close. And then you can kind of visualize that. But you only have one average. So how can you get a variation when you've just got one mean? Well, luckily, there's some theory and some math that goes into it, and you can just calculate it. So we know how much a mean would wiggle if we had lots and lots of them. A sample mean would wiggle if we had lots and lots of them, and that's what the standard error is. So if someone's reporting let's go back. So if someone is reporting a mean, typically they should use the standard error because that's how much means wiggle. If they're reporting some feature about the population, they should report the standard deviation. But you could get anything. I mean, you read this. You'll see mean plus or minus anything. So you have to really be careful that you know, you see that and it's what you expect or whatever. Okay, press on, press on, press on. Okay, so then of course, people, once we talk about standard deviations and standard errors, they often ask me, what's the difference between a mean and a median? Well, you know, basically it's the mean is affected by outliers. the median is not affected. They're both one-number summaries of a whole data set, like peak vertical force. If you had to take 40 dogs, peak vertical forces, and give me one number that represents them, because we just can't write down the whole list of 40. You need one number. What would that number be? And so you have sort of three choices, really two. That's the mean or the median. And if there's some outliers in there, if a few dogs just never got better or three-legged lame through the whole study, so you have this kind of tail, then you'd have to do the median. Otherwise, it would be the mean. Where I really saw this is when I worked in health services research at a teaching hospital in a city, and the poor people in that city would use the emergency room for their primary care. So you'd see lots and lots of like $150 charges, you know. And so when you had a graph like this, there'd be this huge peak for lots of money. And then you have a few people that have these $10,000 fees for something bad happened to them. And they're in the emergency room, and it cost them $10,000 in the emergency room. So you'd have this huge tail. So how do you represent the sort of typical cost of an emergency room visit there? If you take the average, it's being influenced by these $10,000 charges. So that's no good. So, probably. So then you would take the median, and then the median, always half the data is to the left, half the data is to the right. So you could put in $1 million charge and it wouldn't change the median. So again, be careful, because if the data looks skewed, if they have a plot and they're using the mean. So the question is why don't we always use the median? Because they're actually the same when it's symmetric. So why would we just always use the median? When it's symmetric, it's the same. And when it's skewed, the median's better. Why do we even report the mean? Ever? I suspect it's because of history. Before computers, everything had to be done, mathematically, formulas and so on. And all the math for means is much easier than for medians. If the golden age of statistics, which was 100 years ago, if it were now, I think we wouldn't do things nearly the same way. Okay, so then the thing is, the next little quantity that we see a lot of is confidence intervals. So what's a confidence interval? This is easy to explain. A confidence interval is a set of plausible values for a population parameter. So if we think about how we used a median or a mean for the peak vertical forces, you might say, well, wait a second. That's not really just one number to describe the whole thing. Well, we can actually give a whole set of numbers, and that would be a confidence interval. How a confidence interval, the interpretation of a confidence interval is this. So imagine peak vertical forces of the whole population, not the sample. So this is all the dogs that have had TPLOs. There's some mean peak vertical force. We don't know what it is, because it's the population. We just have the sample 40. So what we want to do is we want to, instead of just saying, well, the TPLO group was a 48, so maybe that's close to this, we might want to give a range of values instead. That's the confidence interval. And so we give a lower bound and an upper bound and hope that our true value is somewhere in there. So when you see confidence interval, that's what that is. Now, you often see you probably only see a 95% confidence interval. What that means is that if we were to make 100, if we were to draw 100 samples from our population, if we could, they would cover the mean, the true mean, 95 times out of 100. 5 times we're wrong. So here's a confidence interval where we said, hey, the population mean of peak vertical force is somewhere in here, and it wasn't. Here's another one. So the confidence interval, it's only in there, if it's 95% confidence interval, it's only in there, when I say it, I mean the mean peak vertical force of the population 95 out of 100 times. So you can be pretty confident that your confidence interval is in there. So this is important because you read the paper, and they'll talk about their p-values and so on, and then they might have a confidence interval. Well, what if that confidence interval, this happens all the time, the confidence interval is big. So if I told you that here's a sample of heights out of London, and sorry, I've got to use feet and inches, this is just the way it goes. And in this room, and we'll use the data in this room, the heights in this room, goes from, let's say, 5.5 feet to 6.5 feet. You'd be like, oh, all right. If I said it went from 4 feet to 10 feet, Well, I'm pretty darn sure the average height in London is between 4 feet and 10 feet. It's a pretty useless confidence interval. And you'll find that a lot in papers. If you look at the confidence interval, it'll be huge. And they don't mention it. They'll say that the mean of this group is this and the mean of this group is that. Just think of Wanda's means. One was 48, one was 37. What if I said the confidence interval for the 37 was 20 to 60? You know, well then it's like, and the other one was about the same. You'd be like, well, those are so big. Those are all plausible values. I can't make heads or tails, and that's exactly right. Anyway, confidence interval. Sometimes confidence intervals, which I've represented by the red parentheses, cover an important number like 0 or a 1 sometimes. And so if this is a confidence interval for a difference in means, and it covers 0, that means 0 is a plausible value for a difference, and then it means that those means probably aren't different. Sometimes they overlap, like this might be the extra cap group, and this might be the TPLO group. And when they share plausible values, that's often a sign that they're not really different. So just one of those little things to put in the arsenal. A few more facts, because these can get mired up, and then we're almost into stuff that's not quite so technical. People often report the confidence interval as the sample mean plus or minus 2 standard errors. So that's the classic way. So here we've got mean plus or minus 1 standard error in Wanda's paper. So these are not confidence intervals. So just because you see bars on a graph doesn't mean they're true confidence intervals. They're just, when I gave this lecture before, someone asked me, well, why didn't you put in 2 standard errors? And I think the reason why is if we did, these are, well, I was about to say these are statistically different. So these groups at this time point were different. They got the asterisks. But if I were to put on big confidence intervals, they would touch. If I were to use 2 instead of 1, they would touch. And reviewers are sure to see that and say, hey, there's a problem. Because when confidence intervals touch, like the other side, usually that's a sign that there isn't a difference. So I bet we did it with 2, and then we thought we'd have a marketing issue. And so we went with 1. Right? And 1's not it's not like we're the only people who've done 1. This is commonly done. I'm just saying, when you see these, just don't think those are confidence intervals. Just understand what you're reading is pretty much it. Also, often these ones, they're symmetric. So they're symmetric around the mean. And often, for means, they are symmetric. But for other parameters like odds ratios, they're not going to be symmetric. So just be aware of that. I've gave the Smith and Jones example. Okay. So now we're changing gears again. We're almost done, and then it's cookie time. The last part of this, so let's see, I've done p-values, I've done effect sizes, and now I'm going to do evidentiary value. So this is the last part, and this is the easiest part. Save the easy part for the end. I actually went from hardest to easiest. So now we can talk. So now we're at a place where we can talk about the effect size and whether or not there's the magnitude of the effect in a paper. So you're reading the paper, you're like, oh, look at this. This is this paper. It's like Wanda's paper. There's this huge effect. It's great. The p-value is small. It looks like I should absolutely go back to my practice and start doing TPLOs tomorrow, even though I got to buy a bunch of stuff. I should do it. Well, the problem is it might have this small p-value. It might have this huge effect size, and the paper might be complete junk, even though it reads just fine. And the reason why is that that paper may have weak evidentiary value. And so study designs are all about controlling bias. And just like in a court of law, DNA evidence is the least biased, and a character witness is the most biased. And you certainly rank them. It doesn't matter how many character witnesses you have, at least in the United States, if you've got DNA evidence, done deal, right? Because we know this is like super biased, and that's unbiased, usually. And I'm sure you've seen the evidence pyramid many, many times. This is another evidence pyramid. But the idea, of course, is that it's all about controlling bias. And if you're up here, every effort in the study design has been made to control bias. And down here, biases creep in, creep in, creep in, creep in, creep in, creep in. And so, except for this last one, because animal research, of course they mean like lab animals. And so, not even applicable. So anyway, biases creep in. So the idea is that even though in Wanda's case, let's suppose she had great p-value, great effect size, it had been down here. So the study design was a kind that let a lot of biases in. You still might just chuck it, or really take it with a grain of salt. And of course, and I should say just back here for a second, I have a couple more minutes. Especially, well, I will go ahead one. Oh, wrong way. So, of course, a randomized controlled study beats a retrospective study. And I've probably been a co-author on 50 retrospective studies. And I can always get a p less than 0.05 on a retrospective study. Always. So virtually every, yeah, I just can. And the reason why is because there's a couple of reasons why. But when you have a retrospective study, first of all these biases creep in. They may not be blinded because you didn't blind them. Didn't blind anybody when you didn't think about the study 2 years ago when you got the data and put it in your computer. So you didn't plan on doing a study. These are just cases. So nothing's blinded. Nothing's randomized. There's a selection bias because who knows why one set of clients chose clients with more money maybe chose TPLOs, and the clients with less money chose a less expensive procedure, right? So you have all these other problems. Plus, in a retrospective study, it's pretty easy to go in. I do this all the time. I'll go in and okay, nothing significant. No p-values below 0.05, and they really want a p-value below 0.05. So they come back to me and say, well, we kind of included these patients, and they're being honest. They're truly being honest because everything I'm saying is valid. But the process is not valid. So each step of what I'm explaining is okay, but as a group, as a set, it's bad. So they go and they say, we should not have included these dogs because that was a different surgeon back when. Okay, fine. Take those ones out. P-value, what's that? Still above 0.05. Okay. Well, we picked this cutoff for lameness. And really, there's more than one cutoff you could pick. So we'll pick this one. Try it again. Still not right. Okay, then I try a different statistical method. Hey, P is now below 0.05. Right? And so really nothing every step is kind of valid because, sure, those patients probably shouldn't have been in there. And maybe, but anyway, it's a complete disaster. So if Wanda's study, which was a randomized controlled trial, had been a retrospective and you'd seen this great effect size, super p-value, you still would be like, maybe I shouldn't just go out and all of a sudden buy a TPLO set. Now, this is where it gets hard. I had this conversation just a few days ago with somebody. What if you've got a randomized controlled trial? So now you're a reader and you're doing a appraisal of the literature, like a knowledge summary for us, and you've done your literature review. You've got your search, you've got your papers. There's one randomized controlled trial and 3 retrospectives, and these agree, and that does not agree with these 3. It could be the other direction too, but whatever. Let's say. So what do you do? Right? This is, in my mind, and you can make your decisions. The guy I was talking to is a very experienced researcher, been in evidence-based medicine for a long time, and it was 3 versus 1. And he was like, wow, I didn't know what to do, blah, blah, blah. And my mind is you've got 3 character witnesses and close, not really DNA evidence, but a lot close, you know what I mean? So that's up for you to decide on your own. But I will leave you with, this slide. This is one of my last slides. This is from way back in 2001, a study of, I think, about 36 studies of transcutaneous nerve stimulation to reduce acute pain after surgery. Okay? So there were some randomized trials and some non-randomized trials. The non-randomized ones, like the observational ones, were overwhelmingly positive. It really worked. Awesome stuff. The randomized ones were overwhelmingly negative. And what's interesting is when I saw this, when I saw this recently, I just read a bunch of things on something called p-hacking, which is what I do on observational studies to get a p below 0.05. It's like they have a name for it now. That's how bad it is. And I realized, I'm sure that's what these guys did. I'm sure these guys went in, and they're so desperate to get a 0.05 that they would sort of do anything legal other than like fabricating data to get one that's below 0.05. So you have this huge stack of ones, and then when it didn't work, they were all wrong. Like these are surely wrong, and only 12% wrong. So you can see this is where I come from, and why I think that we should definitely slowly in veterinary medicine maybe get away from retrospective studies. But anyway, you can make your own decision on that, and then I'm done. Thank you. Thanks. I should be able to beat the other crowd up for cookies if they keep questions short. So nothing. You can grab me upstairs too if you want to ask any questions. Oh.
Rich, great talk. Is that on? Can you go back to the soccer? You and I would call it soccer, but most other people in this room might call it football.
Yeah.
So they're very different outcomes that they see, but they're all still above that equally likely line, aren't they? So they're not vastly...
They're not vastly, right. Oh, I mean, some of the intervals, are big. Well, take these two. Take these two, this one's statistically significant, this one is not. So if you're going just on, but you're right. I mean, they're not, it depends on what you're looking for.
It's keeping in mind that there may be lots of different ways to do these things, and sometimes people will find vastly different. It just makes it complicated, doesn't it?
Well, actually, your point's really well taken, and that is this really goes again to the point of don't worry about it too much, because except for these two, she's really right. They all got different answers, but really kind of close ones. These are all kind of, they're probably similar enough for clinical practice, right? I mean, they're not, And so if you're to calculate, effect sizes from these, they'd all be about the same probably. So even though they're different, I think Kristen's right. They are pretty similar. And that's why, again, even more reason not to worry about the stats too much. If you think they're wrong, then say something. But if the stats look right to you, then maybe it's this one, or maybe it's this one, or maybe it's this one, or maybe it's this one. But you're not going to, that's not the difference between this one and this one, usually. So, yeah, thanks. I think there's another.
Yeah, it seems to me if research...
Sorry, we need it.
Oh,
yeah.
We got evening here. Hi. It seems to me if researchers aren't going on to look at effect size and and sort of understanding what they found, then you kind of think the conclusions they're drawing from their studies, can they draw valid conclusions if they're not looking at that? Should the onus not be on the journal that's publishing the paper to sort of set that as a criteria that the authors have to look at that and make it part of the whole study?
Yep, absolutely, yeah.
It seems strange that it's us, sort of the consumers of the material, that are having to do that to judge its validity. It feels like it should be further up the process. Yeah,
and I think for the journal that we have, that we're starting, I'm going to talk about it in a little bit, another hour or so. We're going to try and ask authors of primary research to include a few effect sizes. And in fact, it's interesting, on that same paper, I don't know if I said this in this talk or not, but on Wanda's paper, she just even asked me last week if she could rewrite the paper with effect sizes in there, if it was legal, like legit. Like, what would people think if she just took that whole paper, rewrote it with the effect sizes, and mentioned the p-values, but all about that part of it, the effect size part. And I said, well, I've never seen that done. It's kind of like doing two papers from one data set, and but I thought it was an awesome idea. And, it's up to her if she wants to put that 2 rows in her CV or one. That's her ethical issue, not mine. So yeah, you're right. I think it is really on them. And that one psychology journal now, I forget the name of it, they're saying no p-values to effect sizes. So. All right, thank you.